All right, continuing on with the periodic trends, we have a ionic radius. First of all, cations are always smaller than the atoms they form from. This isn't always true, but it says because the electrons that are lost come from the valence level. Not always true. So when you remove an electron from something, the remaining electrons experience a greater attraction to the nucleus because there's less of them to be pulled on by the nucleus, and therefore are brought in closer to the center of the atom, or in this case, the ion. So every electron you remove causes the ion to become smaller and smaller. The opposite's also true. Anions are always larger than the atoms they form from. When you add an electron to something, that increases the amount of interelectronic repulsions. The nucleus cannot pull as well on a larger number of electrons compared to a smaller number of electrons. So both of these things together cause the radius to increase. All cations and anions increase in size as you go down a group, meaning that K plus, for example, is bigger than Na plus, and Rb plus is bigger than K plus. And this has to do, again, same with atomic radius. The remaining electrons, those valence electrons, which are now in a p sublevel, are in a higher energy level. So the alkali metals will lose their valence electron from the s sublevel. Remaining electrons in those +1 ions are in the p sublevel. A higher energy sublevel, or sorry, higher energy level as you go down within that group. Radii of isoelectronic species. Isoelectronic means same number of electrons. For example, Na plus and Mg plus 2. Both of those have 10 electrons. Radii of isoelectronic species decrease in size as the nuclear charge increases. So Mg plus 2 is smaller than Na plus because Mg plus 2 has 12 protons in its nucleus. Na plus only has 11. So that greater nuclear charge allows for the 10 electrons to be pulled in closer to the center, resulting in a smaller radius for Mg plus 2 as opposed to Na plus. Go to page 230. We can see on the left side comparison of neutral atoms shown in green to the ion, cation shown in blue. So neutral atom is always going to be bigger, cation is always going to be smaller. On the right side, we see neutral atom green and anion red. And we see again that for any particular substance, its anion will be bigger than the neutral atom. Take a look on page 231, example 6.4. First three we're going to compare are calcium ion, potassium ion, and aluminum's ion. Now right away you should see that aluminum ion is the smallest. It has its outermost electrons. Even if you look at the neutral atom, and then it's going to be the same for the ion, aluminum, the neutral atom, has its valence electrons in the third energy level, whereas both calcium and potassium, the neutral atoms, have their valence electrons in the fourth energy level. So their ions, too, we see that same thing where aluminum has its outermost electrons, in this case, the second energy level for Al plus 3. Both Ca plus 2 and K plus have their outermost electrons in the third energy level. So that makes Al plus 3 the smallest. And then between Ca plus 2 and K plus, they're isoelectronic. And so since Ca plus 2 has a greater nuclear charge, it will be smaller. So Al plus 3, Ca plus 2, and K plus. And then for letter B, we're comparing Se minus 2, Br minus, and Te minus 2. So Te has its outermost electrons in the highest energy level. That would be the fifth energy level, which makes Te minus 2 the biggest. And then between Se minus 2 and Br minus, Br has a greater nuclear charge. So Br minus will be smaller than Se minus 2. So we get Br minus, Se minus 2, and then Te minus 2. Go to page 247. Try number 36 on your own. Pause the video, please. So for letter A, all of those neutral atoms we'll compare first have their valence electrons in the same energy level. Gallium has the highest nuclear charge, therefore it'll be the smallest. Potassium has the lowest nuclear charge, therefore it'll be the largest. And then for letter B, again comparing the neutral atoms, all of those are in the same group. And so atomic radius increases as you go down. So same for the ions. So beryllium's ion would be the smallest, and barium's ion would be the largest. And our last trend is electronegativity. Be careful, don't confuse electronegativity with electron affinity. They're a little bit different. Electron affinity has to do with individual atoms gaining electrons to become negative ions. Electronegativity is a little bit different. Here's what the definition says. It is the tendency of an atom when it's bonded to another atom to attract electrons. The most simple case I can show you is this. When you have a fluorine atom bonded to a hydrogen atom, so that little line there represents a covalent bond. Fluorine is more electronegative, so it's going to pull on those shared electrons, pull them closer to fluorine's own nucleus and a little bit away from hydrogen. Now, it's not going to pull the electrons off of hydrogen, so it's not like it's gaining those electrons. It just has a greater attraction for the shared electrons than does hydrogen. So general trend, electronegativity increases as you go up and to the right. This excludes the noble gases. And so the element with the highest electronegativity is fluorine. There's a table in your book on page 232. Something you may notice is that there are a lot of exceptions to this trend. So the general trend increasing up and to the right. Just know that there are a lot of exceptions, and you don't need to know why those exceptions in this case exist. So just want to make you aware of that. Take a look at the bottom of the page. We're going to compare boron, sodium, fluorine, and oxygen. This works pretty closely with the predicted trend. So sodium is the furthest to the left. We'd expect its electronegativity to be the lowest. Fluorine is furthest to the right. We'd expect its electronegativity to be the highest. And that is what we see in this example. So again, there'll be a book question where it's better if you use the table 6-3 to answer that question, because there are a few that do not follow the trend. All right, so that completes part 2 of periodic trends. Next time, we'll talk about some other chemical reactions other than what we learned last unit. All right, thank you.